Hello, class. So this is just the answers. I'm gonna go back and answer some of them, especially this one because I know that one is quite difficult. Units. So you must show. So these are just the answers. You do need to show work to get full credit. If you're really stumped, this is definitely something you should come and ask me Monday. I'll be at school late on Monday. So you can come back later for full solutions to some of the problems. I'll try to mark which ones. Maybe I'll do more, maybe I'll do less. I don't know. Yes, I'm sick, which is why no, I'm not done grading, but I figure I better put these out before noon on Sunday. So these are the answers for this page. I'll go up and put up a different page. Oops, and this is a comma for anyone that's wondering. It is 141,610 joules, not 141 point. Alright, so this is the first page. These are the answers for these ones right here. I've already made a video going over all of them. Personally, I think this one and this one are the hardest mathematically, and this is the hardest one conceptually. Okay, this is the second page. These are the answers. If I was grading this for your response, depending on how you explain it, it could be both, but since this is multiple choice, it would probably be the first one because that implies there is no net force on the objects, which says it's in equilibrium. Remember, this is what we talked about in class. It's definitely the wall because it bounces back. Remember, this is a video. If I'm going too fast, pause it. Alright, these are the answer for, I believe this is page number 4. We did all of these in class for the most part, so I'm probably not going to go over any of these. Alright, this one I'm going to explain a little bit more. I'm probably going to go over some of these in more detail. Most likely these because I want to make sure you really get it. And this one because I think it's the most difficult one on here. This one, in case all you need is a little hint, it has to do with the angles. Make sure you draw a free body diagram. Remember, normal force, or F normal, is always at a right angle, and gravity is always straight down. Which means if you want to know how much this is, you have to solve it knowing that that is a 25 degrees. And then looking at the energy one at the bottom, an example of this, you could think of it maybe like a frictionless pool table. And then for a situation where energy is not conserved, and you can think of this also as bouncing perfectly, this it would be 6 together. Sorry, I'm writing down at the bottom of my tablet and it's not getting that as well. And the last one, we haven't really used it as much because it's hard to set up, but it is a stroboscopic camera. Hopefully we will have a chance to use those in the next semester. Next page. So the first one is times 4. Force, the next one, forces towards the center. And there's no change in speed because conservation of energy. Momentum is P equals mv. The force, that's if there's no friction. If you're on ice, drive very slow because there's not a lot of force unless it's a very banked curve. But the reason they do have banked curves is now when it's banked, now your normal force is helping you turn. The next one is 20 newtons. And for this one, in case you can't tell, the arrow's this way. The two parts that would go into this are a part that goes this way and a part that goes this way. So in layman's terms, we could have you need a graph that looks like this, and you would need a graph that looks like that. Alright, this is the second one. Remember, you must show work for these. I thought this was the trickiest one. On here, hopefully these answers make sense. Pause them, check your work, try to figure them out, how I got them, and I'm moving on to the next page. Alright, for this first one, it's just a basic momentum problem. This is one of the harder conservation momentum problems. You have to do a before and after, and there's 1 and 2 things going on in each one, and you have to set all of them equal to each other and add the 1 and 2s. That doesn't make sense. I might make a video. I'm running out of time to finish everything today. This is my into my first hour working on this video, even though it's only 6 minutes long. In the flower pot, you can use either one of these, probably find the right kinematics equation. This one you just have to know what it means. This is the force of gravity equation. And this is a easier conservation of momentum. You're essentially going to use the same formula. Alright, if you're still working things out, pause it. I'm moving on to the next one. And here we are on the last page. So it's definitely Xandra. Why? Think about their masses and which one would have more energy. This one, is it actually moving and therefore can't have momentum? This one, in case you couldn't tell, the lighter one is the yellow car, and this is another dual before and after conservation of momentum. This amount must equal that amount. And this one I'm going to draw out for the last one. So remember, the centripetal force is always towards the center. And in this case, since its circle would probably look something like this, at this point in its rotation, it's going to go directly this way at a 90-degree angle to the center line. Alright, hopefully this was helpful. I'll be trying to release as much videos as I can today, but remember, yes, I'm sick. I'll be there tomorrow. I'll be there tomorrow. Anyway, hopefully this was helpful, and I'll see you guys tomorrow.